And conditional probability is red. You'll see it has a vertical bar in it. This means the probability of F given E. So it's the probability of one thing happening if I already know something else occurred. Okay, so it might be the probability of, let's see, the seniors showing up at the softball game given that it is senior night. So I already know it's a senior night. What's the probability that the senior girls show up? Okay, so something has already occurred. An easy example to kind of show the difference between regular probability and conditional probability is using a dice. So if I just roll a dice, what is the probability of me getting a 4? 1 in 6. There are 6 sides of the dice. We know one of those is a 4. So that's 1 in 6. Okay, but what if I roll it and I say, oh, I got an even number. What's the probability of me having a 4?
1/3.
Why?
Because there's only 3 even numbers.
I know, my dice still has 6 sides, but I already rolled it, and I told you that it's even. So even though it has 6 sides, I know there's only 3 options. I could have gotten a 2, or a 4, or a 6. So now the probability of me having that 4 becomes 1 in 3, because I know a condition already occurred. What if I rolled it and I said, I got an odd. What's the probability I rolled a 4?
0.
0. So the probability of rolling that 4 has changed given what I already know. Right? When you're looking at, when we set up our probabilities, which part of this fraction changed? The numerator or denominator? Denominator, because I'm no longer looking at the entire group. It's a smaller section of it because I know one thing already happened. With conditional probability, so if you're following along on your formula sheet, to find a conditional probability, it's the probability that both things occur divided by the probability of E. Right, so the probability of me having a 4 and an even number divided by the probability of having an even number. All right, so we can look at conditionals using this formula, which we'll do more later on. We can also just do it if we have like rolling dice or when we have tables, we're just dividing as we have before. It's the same for not, so the probability of not both things occurring divided by the probability of not one. I put this on here because it's on the formula sheet, your book talks about it, but really when we do conditional, we're going to stick with this. All right. Let's look at some examples from tables first. I think that's a little bit easier to understand, and then we'll get into some scenarios. So this was from a survey. 1,017 adult Americans were asked about their beliefs in a higher power. So you can see they have the results broken down by geographic region and their answers. What is the probability that a randomly selected adult American who lives in the East believes in God? All right, so let's practice our notation. I'm asking for probability that someone who lives in the East believes in God. So I'm asking for the probability that they believe, given, what do I already know? They are from the East. All right. So do I have to look at the entire table here? No. I know that the person is from the East. So when I'm setting up my denominator, I'm only looking at the East. So we need our total. Add all those up. 255. So that's our denominator. Because I'm not looking at every person in my survey, just the people that were from the East. And then we're still just looking at that row. Conditional, we're ignoring the rest of the table. My numerator, I want the people that said, yes, I believe. So how many of those? So 204 divided by 255. And we get 0.8. So an 80% chance that if they were from the east, they said they believed. Is that okay? Let's look at the next one. What's the probability that a randomly selected adult American who believes in God lives in the east? How is? Yeah, I changed what I knew about that person already. So what's the given? What do I already know? He said they believed in God. Okay. And then what's the other thing that I'm trying to find out? If I know that they said they believe in God, I want to find out the probability that they were from the east. Right. So my condition. This time, my condition is that they said they believed in God. So I'm only looking at these people from my table. So my total, my denominator, is what I get when I add all of those up. And then from those, how many were from the east? And so we get 0.2592. Very different from the first one. First one was an 80%. This one was not quite 26%. So you have to pay attention to your conditional. Once you know your condition, that is the only portion you are looking at, because we already know that is true. Any questions on that one? Okay, so let's try to look at one where I don't have it broken down. I'm just giving you a scenario. In 2005, 19.1% of all murder victims were between the ages of 20 and 24 years old. Also in 2005, 16.6% of all murder victims were 20 to 24-year-old males. So I have this many were between 20 to 24, and this many were 20 to 24-year-old males. What's the probability that a randomly selected murder victim in 2005 was a male, given that the victim was 20 to 24? So I'm trying to find the probability of a male, given I already know they were 20 to 24 years old. And this is where your formula sheet comes in so handy, because you know I'm going to let you have it on every test or quiz. So if I were doing this and I write down what I need, and I'm looking my conditional probability rule, and it tells me the formula is the probability of E and F, so that's probability of male and 20 to 24, divided by the probability of what? E. And E was my condition, which in this case my condition was 20 to 24. So divided by the probability they were 20 to 24. Alright, looking back at my problem, what was the probability that they were male and 20 to 24 years old? 16.6%, so 0.166. Divided by, what is the probability that the person was 20 to 24 years old? So if you divide those, I really encourage you guys to try to write out your formulas like this. It makes it so much easier when you are working a problem and trying to figure out where to plug in these numbers if you have that formula written out. And then we can kind of make sense of where things go. Alright, any questions on that one? Okay, so yesterday we talked about independence. And we said that if events were independent, that meant that the probability of knowing one thing happened was the same as the regular probability, right? So the probability of me wearing a shirt with stripes on it today and the probability that you get sick, those are totally unrelated, right? So knowing what shirt I chose to wear to school today, did that change the probability of knowing? No. So that means that the probability of E given F was the same as the regular probability. The probability of you getting sick is the same as the probability of you getting sick if I wear this shirt to school. So conditional probability is the same as regular probability if we're dealing with independent events. So yesterday when we did our multiplication rule, we said we were just able to multiply because we were dealing with independence. If we do not have independent events, our multiplication rule becomes the probability of E times the probability of F given that E already occurred. Right? So it adds an extra thing to it. We can't just straight multiply the two probabilities. We have to look at the condition. So we're going to try to apply this to a few problems. All right, so same scenario here with the murder victims, so same percentages. But this time I want, what is the probability that a randomly selected murder victim in 2005 was a 20 to 24-year-old male? So I'm finding the probability that we have a male and 20 to 24 years old. Okay, and we said at the beginning of class and yesterday, when I say and, what does that mean? Multiply. Okay. Are these things independent, being a male and being 20 to 24? Are they independent? Not in this scenario. So we have to think of it as a conditional probability. This is the probability of male times the probability, okay, we're thinking about our formula, probability of the first times the probability of the second given the first. So times probability of 20 to 24 given that they were male. Now, sometimes in our problem, things may not be in this order. My conditional, this is saying that I have to know if they're a male, the probability that they were 20 to 24 year old. We found the last one, the 86.9 is probability that they were male given 20 to 24. Okay, so you see in the problem, the condition that I told you was the 20 to 24. So is that the same as this? No. But let me ask this question. At the beginning, if I had wrote this down as a probability of being 20 to 24 and a male, is that the same as male and 20 to 24? Yeah. And if I set it up that way, the probability of the first times the probability of the second given the first, then do I have the information that I need? Yes. So you have to be a little bit careful with these ands. You're multiplying by a conditional probability. So you have to think about which conditional probability I gave you in the problem. But we know we can flip the first and second things. So we could technically use either of these, but I need to use the second one because the condition that I gave you was the 20 to 24. Alright, so from this, what was the probability of being 20 to 24 years old? 19.1, so 0.191 times the probability of being male given they were 20 to 24. 869. So the probability of being both, 16597, so that's 16.60%. So you can see these are starting to get a little harder. Writing down that formula is going to help us. Trying to organize the information. Looking back in the problem, I just threw a bunch of numbers at you. So we need to take a second to figure out what we have and where we're going to plug it in. Any questions on that one? We're going to try a few more together. And remember, we're practicing this for several days to come. So it's not just going to be an instantaneous thing. We're going to practice. Suppose that of 100 circuits sent to a manufacturing plant, 5 are defective. The plant manager receiving the circuits randomly selects 2 and tests them. If they both work, she will accept the shipment. What is the probability that she would reject the shipment? All right. So what would cause her to reject this? If one of them is defective. So it could be the first one is bad and the second one isn't. Or the first one's good and the second one's bad. What about if both of them are bad? Yeah. So would it be easier to find the probability that she accepts it or the probability that she rejects it? Okay, there's only one scenario where she accepts it, right? They both have to be good. So that would probably be the easier route because we just have to find the probability of them both being good. Then how do we turn that into the probability that she rejects it? 1 minus, that's the complement, like we've been talking about. Okay, so let's find the probability that she accepts this. Okay, so we know that the only way she accepts it, you guys told me, was if they're both good. So if they both work. So the probability the first one works and the second one works, right? Maybe I should say probably the first works and the second works. Okay. So if we use our conditional formula, the probability of both things happening is the probability of the first times the probability of the second, given the first one already worked. Okay, that's the AND formula that we wrote down or that we have in our notes packet for the general multiplication. All right, so the first one working. How many we have? How many total circuits? 100. So that's my denominator. Out of those, how many work? 95. Okay, so what happened? The inspector came, she took one out, she tested it, it worked, she said to the side. So given that the first one already worked, when she went back, how many circuits do we have? We have 99 now, because we already took one of those out. Right, out of those 99, how many of them work? 94. because we're already assuming that the first one we took out worked. So I took out one working one, so there would be 94 remaining. Okay, let's multiply. So the probability that she would accept this is 0.893. Oh, did I mistype something? Yes, I did. Yeah, I accidentally mistyped the number. How about 0.902? Is that better? Thank you, guys. So then how do we find the probability that she rejects? Mm-hmm. And we get there's a 9.8% chance that this shipment would get rejected. All right. Let's try another one along those lines. Of 3,215 individuals surveyed, 130 agreed with a recent bond issue. Suppose that we randomly select one. What is the probability he or she agreed? So the probability that one person agreed. What do I do? This is just kind of like our first day. Just dividing. We only have the one person to consider. We already said 130 of those agreed, so 130 out of our total. And we get 0.0404. Right. If two individuals are selected, what is the probability they both agreed? So the first one agreed and the second one agreed. So and means I'm going to be doing what? Multiplying. What's the probability the first person agreed? Now you can use the decimal. I'll go ahead and just use a fraction so I don't have rounding error. Okay. If I've already talked to that one person, are we going to go talk to that same person again? No, so that person has been excluded. So how many of the people remaining agree? 129. Out of how many total people remaining? Okay. I'm going to leave a few extra decimal places this time. 0.001623. So it's a pretty unlikely that they both agree. What do we call that? Unusual. Anything less than 5% is unusual. How many times have I asked you guys that? Maybe it's going to stick. We get it. All right, C. Compute the probability of two individuals agreeing, assuming independence. Okay. What we just did was assuming they were not independent. But this one saying independence, that's like saying, okay, I sent a random survey out and one person said they agreed, and then I'm going to send another random survey out. Is it possible that the same person could have answered both surveys? Yes. So if I'm assuming independence, that's assuming that even if the first person agreed, that didn't change the probability of the second one. So what would I do in this case? We don't change the numbers, or you could think of it as squared. We just have the same thing twice. that's more like what we were doing yesterday. And we get a very, very similar probability. Just slightly different. In general, this isn't going to affect us for several more chapters, but we will assume that if our sample is less than 5% of the whole population, we will assume they are independent. That comes into play several chapters from now, and we'll talk about it a lot more then. But that is just something we'll mention later on. All right, so I have one final example, and then I want to give you guys a chance to practice and ask questions. Suppose a computer chip company just shipped 10,000 computer chips to a computer company. Unfortunately, 50 are defective. Take a second and see if you can set up this probability for me. I want the probability that 2 randomly selected chips are defective using conditional probability.
I'm
Maybe.
betting Lucy's house that these answers
I got 4.
Lucy's house. Okay.
come.
Game on. Let's see. All right. So I want the probability that 2 are defective. So the first is defective and the second is defective. Okay. So we know that's the probability the first is defective times the probability the second is defective given that the first was. All right. What's the probability of the first one being defective?
50 of them.
All right, 50 of them are bad out of the 10,000. All right, the conditional probability times. If the first one was defective, now how many do I have if I took out one of the defective ones?
49.
49 defective ones out of how many total?
9,999.
Okay, so this gives us 2.45, and then you see E negative 5. That's your scientific notation. Move your decimal back 5 places. So, going to be very, very unusual for us to get 2 defective chips there. All right. Compute the probability that they are defective using independent events. What does it mean if they're independent? Right. Maybe I have 2 people that are both checking the shipment, and they each just go in and select one and test it. Is it possible that they selected the same one? Yes. So it's just 50 over 10,000 times 50 over 10,000. And so we get 2.5 e to the negative 5. So it looks like that. All right. Any questions there? The last slide that I have is practice with finding probabilities, and I think I'm going to do that one at the beginning of class tomorrow because we're just going to be putting more things together. So your assignment out of the book, same rules we've been using. If it says find and interpret probability, you don't have to interpret. 29 says to draw a tree diagram. You do not have to unless you want to.